back to this video series on algorithms and algorithm analysis. In this supplemental part, we'll introduce additional asymptotic notations that are used in computer science. Here's the definition of big O again. Recall that a function f of n is big O of g of n if there is a positive constant c such that after a certain point n naught, f of n is bounded above by c times g of n. That is, big O provides an asymptotic upper bound relationship between two functions. Another asymptotic notation is big omega. The definition is virtually identical, except for the direction of the inequality. Formally, f of n is big omega of g of n if there is a positive constant c and an integer n naught such that for all integers n greater than or equal to n naught, f of n is greater than c times g sub n. Or f of n is bounded from below. We write similar notation, except that we use a capital Greek letter omega. Big omega characterizes the inverse relationship. That is, g sub n represents an asymptotic lower bound to f of n. Another asymptotic notation is big theta. Big theta gives both an asymptotic upper bound and an asymptotic lower bound, proving an asymptotic equivalence between the two functions. Formally, f of n is big theta of g if there are two constants, c1 and c2, and an integer n naught such that for all n greater than or equal to n naught, f of n can be bounded both below and above by these constants times g. We use the capital Greek letter theta in our notation. This equivalence basically means that both f and g grow at the same rate. We can now make some observations about the relationships between big O, omega, and theta. First, big O and big omega complement each other. F of n is big O of g of n if and only if g of n is big omega of f of n. Big theta implies that both relationships hold. That is, f of n is theta of g of n if and only if f of n is big O of g and f of n is big omega of g. Again, big theta provides an equivalence. F of n is big theta of g of n if and only if g of n is also big theta of f of n. In this manner, big theta provides a tighter characterization than just big O. For example, n is big O of n, but it is also the case that n is big O of n squared. Big O does not need to be a tight characterization. However, with theta, you don't have these loose characterizations. N is big theta of n, but n is not big theta of n squared. Another, though less common notation, is soft O notation. Frequently, algorithm analysis may involve logarithmic terms. However, these terms are very slow growing compared to the higher order terms. Soft O notation, using a tilde above the O, allows you to ignore those lower order or logarithmic terms and focus on higher order terms. For example, n log n, a common quasi-linear function arising from algorithm analysis, can be simplified to n using soft O notation and ignoring the logarithmic factor. We've been using big asymptotic notations, and indeed there are small asymptotic notations. Small o and small omega notation also exist. Formally, the definition involves either defining an epsilon n pair, or there's an equivalent definition using limits that we present in another supplementary video. The intuition, however, is that while big O provides an asymptotic greater than or equal to characterization, little o is stricter, a greater than but not equal to a characterization. That is, it provides a strict upper bound characterization. It is a stronger statement if two functions have a little o relationship, since they also have a big O relationship. However, the other way around is not true. If f of n is little o of g of n, then we know that the equivalence is in fact not possible. That is, a big theta relationship is excluded. Likewise, small omega notation also exists. The definition is similar but with a reversed inequality. Like the other relationships, big omega provides an asymptotic less than or equal to relationship, while little omega provides a strict less than but not equal to relationship. We note that there's no corresponding little theta notation, as big theta already provides an asymptotic equivalence, while little o and little omega provide a strict asymptotic inequality.